Good morning, students. It's 8 o'clock, so let us start. So, last time we were doing the inventory model. So, last time I was discussing this question. So, the demand of a commodity in a single period has uniform distribution with PDF. Fx is equal to 1 upon 40, x from 0 to 40, otherwise 0. The holding cost is rupee 1 and the stock out cost per unit is rupees 3. The purchase cost is rupee 1. What is the optimal order policy? If the initial inventory is 5 unit, assume that there is no setup cost. So initial inventory is given to you as a 5 units. So it is means I. And no setup cost means K is equal to 0. The cost of placing an order is rupees 10. What is the optimal ordering policy if the initial inventory is 5? In this case, K is given to you as a 10 and this is the initial inventory I. Then determine the general ordering policy in this case. That is, determine the ordering point A such that if I is less than A, initial inventory is less than A, then uh, you have to order R star minus I. If the I is greater than A, then we do not order, assume K is equal to rupees 10. So in this case, first of all, what is given to you? So in this case, first of all, we have the PDF which is uniformly distributed. So it is given to you 1 upon 40, 0 to x to 40, otherwise it is 0. Otherwise it is 0. So for the uniform distribution, you know what is the CDF? CDF is 0. If x is less than 0, it is the x minus 0 upon 40. So it is the x upon 40. If the x from 0 to 40 and it is 1 when x greater than equal to 40. So if we have this, now we know that FR star is what? FR star is C2 minus C0 upon C1 plus C2. C1 plus C2 and C2 is given to you as a stock out cost, unit cost is given to you 3 rupees. Purchase price is given to you 1 rupees. Holding cost is given to you as a 1 rupee and stock out given to you as a, so 2 upon 4, so it is the 1 by 2. FR star is equal to 1 by 2. So FR star from here it is equal to, it means this implies R star upon 40 is equal to 1 by 2. This implies R star is equal to 20. So optimal desired inventory level is r star is equal to 20. Now in the first part we have computed that what is the desired inventory level. Now in the part A, what is the optimal order policy if the initial inventory is 5? Assume that there is no setup cost. When there is no setup cost, it means we are not ordering. So when we are not ordering, at that time what will be the optimal cost? Means they are asking what is the expected total cost when stock is 5. When stock is 5, then what is the optimal cost? So we know that in this there is no setup cost, no purchase cost, only either the holding cost or the shortage cost. So holding cost is what? Because we have the item either the 0 to 5. So how many item you have to hold? 5 minus x and into fx, that is the 1 upon 40 into dx. That much item you have to hold, plus C2, that is the 3 rupees, and how much shortage we can have if the demand is more than the 5 and up to the 40. So what is the number of the shortage? X minus 5, and the probability will be the 1 upon 40 into dx. And here we have the 1 rupees. C1 is given to you as a 1 rupee. So this will come 1 upon 40, and when we integrate, it will come minus 5 minus x whole square by 2, 0 to 5, plus 3 upon 40, and when we integrate, it will give you x minus 5 whole square, x minus 5 whole square by 2, and 5 to 40. So this will give you 1 upon 40, 25 by 2, plus 3 by 40, and here we have the 35 into 35 divided by 2. So on solving, it will give you rupees 46. Rupees 46. Now, in the second part, the cost of placing an order is rupees 10. What is the optimum ordering policy if the initial inventory is 5? So they are asking the cost when you are placing an order. Means they are asking ETCK when the desired inventory level is 20. So at that time, what is the K? K is equal to 10 plus C naught into Q. So how much you have to order? C naught 1 rupees. How much you have to order? 20 minus 5. 20 minus 5, because 5 in your hand and you want the 20. Then after holding cost 1 into how much you have to hold? 0 to 20. 20 minus x 1 upon 40 into dx. Then after the shortage cost, so unit shortage cost is rupees 3, and how much you have to how much we have the shortage? So it is the 20 to 40, 20 to 40, and how much, what is the quantity of the shortage? X minus 20 in 1 upon 40 into dx. It is clear, or I have to rewrite? Plus 3, 20 to 40, x minus 20, 1 upon 40 into dx. So this will come 10 plus 15, 25 plus 1 upon 40, and this will give you minus 20 minus x whole square by 2, and here the limit is 0 to 20 plus 3 upon 40, and here we have the x minus 20 whole square by 2, and it is the 20 to 40. So 25 plus 200 upon 40 plus 3 upon 40 into 200, so it will come the 45. So rupees 45. So what will be the optimum ordering policy from the part A and part B? Optimum ordering policy is place an order, because when we are placing an order, total cost is coming 45. When we are not placing an order, total cost is coming the 46. So optimum ordering policy is what? Place an order, place an order, right? Of quantity r star minus I. So r star is what? 20. Initial inventory is 5. So of the 15 units, of 15 units, you have to place an order. Then the total cost will less. Now, in the in the part C, determine the general ordering policy. What is the general ordering policy? In this case, that is determine the order point A such that if initial inventory less than A, then order the quantity R minus I. If initial inventory more than equal to A, then there is no need for ordering. And you have to take the setup cost as a rupees 10. It means what we have to do? We have to do the, in the part C, ETC. If the quantity in our hand is the A and we are not placing an order, and it must equal to the ETCK when we want our inventory level should be the R star. So when we are not placing an order, at that time there is no setup cost, no purchase cost, only the holding cost. So 0 to A minus X into dx upon 40 plus 3 into A to 40, A to 40 x minus A 1 upon 40 into dx. So you have to bear either the holding cost or the shortage cost. Then after, on the right hand side, when we are placing an order to make the inventory level R star, so how much you have to order? So R star minus A you have to order. So in this case, K is what? 10. 1 into purchase cost. How much quantity you have to purchase? 20 minus A. 20 minus A. And what is the holding cost? 0 to 20. 20 minus X. 20 minus X. 1 upon 40 into dx. Plus shortage cost rupees 3, 20 to 40. And what the quantity of shortage? X minus 20, then required probability 1 upon 40 into dx. So now using this integral equation, we have to determine the ordering point. So here, if you take the 1 upon 40 outside, so inside we have minus A minus X whole square upon 2. Integral limit is the 0 to A plus 3 upon 40 and X minus A whole square upon 2, and here you put A to 40 is equal to 10 plus 20 minus A, 20 minus A plus 20, right? Because this integral already we have solved here, right? This integral already we have solved here, so it is the same integral, right? Means this is the same integral here I have solved. So already we have the 25 plus 20, that is the 45. So here I can write the directly the 20. So it will become 1 upon 40 a square by 2 plus 3 by 80 40 minus a whole square is equal to 50 minus a. 50 minus a. So this can be written as, so here you will get the quadratic equation. So quadratic equation will be the 4a square minus 160a plus 800 is equal to 0. So from here a will come 34.14 and 5.86. 5.86. So what will be the ordering policy? So here, because desired inventory level is 20, so here we consider the A is equal to 5.86. So what is the optimal ordering policy? Optimal ordering policy. What is the optimum ordering policy? So optimum ordering policy is, if I is less than A, place an order, place an order of quantity R star is equal to Q star is equal to R star minus I. If I is greater than equal to A, do not place an order. Do not place an order. So that's why in the part AB, you have observed given initial inventory is 5, which is less than 5.86. So we have placed the order of quantity R star minus 5. That is the 20 units. So that's all in the inventory. Is there any doubt in the part of the inventory? Anything you want to ask in this question? Yes, anyone? Any doubt in this question? So now next chapter is chapter 6 from the EDD notes, reliability. So actually reliability mainly we have used, or it was originated in the Korean War. So reliability is nothing, right? You have the enough idea about the reliability because in day to day you use this word. Anyone can tell what is the reliability? What is the reliable? In behavior, what is the reliable? In machining, what is the reliable? For the instrument, what is the reliable? Yes, anyone? Hope I trust
Sir,
audio
when
video is okay. Yes.
sir, when instrument is said to be reliable, we can assume that the measurement given by it is accurate.
No, first of all, reliable means it is working, it is functioning. Whether accuracy is different thing. Accuracy is different thing. We are talking about the working. So reliability of a device, it may be the system, it may be the subsystem, it may be the component, it may be the unit, anything. So reliability of a device at a point t is the probability that device will operate without failure, performing properly over the interval 0 to t under the specific condition, right? A specific period under the certain specified operating condition, and we denote it by the rt. Means what we are saying that here we have the any timeline. So any product has started from the t is equal to 0, right? Any product, any device is started, right, functioning from t is equal to 0, and at the t is equal to t, at the t is equal to up to the t is equal to t, there is no breakdown. After that we have the breakdown. So up to the t, that device is the reliable. So probability that device, it may be any component, unit, subsystem, system, right, at the time t, means at the time t is the probability that device mm, will operate without failure. Means up to here it is the functioning, up to here it is working, there is no failure. Over the interval 0 to t specified period under the certain specified condition, operating condition, and we denote by the rt. So what is the meaning of the rt in different way? Thus the t is means what we are saying that device is working, it fail at this point. So it means this is what, this is the t, with this t we call as a time to failure. Time to failure means at the time t it is failing, at the time t it is failing. So we say time to failure. So t is what, a continuous random variable. It can be 1 second, it can be 1 minute, it can be 1 year, right? So it is random variable, and time, it is time, so continuous random variable representing the life length of a device. T represent time to failure or life length of a device. Then mathematically reliability is defined as rt is equal to probability that up to the time t it is surviving, life length is more than the but specific time, that is the t, and t should be the positive time. So reliability is nothing, it is the probability that time to failure of a device is more than the specified time, means it is survived up to the specified interval 0 to t. And if you are means if you want to give the relative frequency definition for the reliability, so we can say reliability is what, number of survived machines, a number of the survived device at time t, right, at time t divided by the number total number of the devices we have applied, we have started to use at the time t is equal to 0. Means it is a relative frequency approach or definition for the reliability, that it is the ratio of number of survived device and total number of used device. So at the time t means initially we have the 100 items, and after the 50 days, after 50 days we have only the 75 items working, 75 devices. So it will be the, what will be the reliability, 75 upon 100. So reliability will be the 0.75. So it is already written here, where nt is the number of the device surviving at that instant t, and n0 is equal to n is the number of the devices put to use initially. So Generally, we use the probability definition of the reliability, right, instead of the relative frequency definition. Now, from here, we have the important results. Theorem 6.1. So, reliability, even for the reliability, we are means we in general talk for the human being also, whether the human being is functioning or not, right? For the device, for the any instrument, for everywhere we are nowadays in every means when we are living in the world of the IoT, right, internet of things. So whole the system, whole the network must be the reliable, then only we can perform well. So in that point of view, the reliability is very important. So we have the important theorem 6.1. Reliability function RT satisfy the following properties. So here, first one is reliability is what it when we are talking. So what I have said you that T is what time to failure, time to failure means it is what, it is the random variable, continuous random variable. So when the continuous random variable, it means characterized by PDF and CDF, characterized by probability density function FT and cumulative distribution function FT, characterized by the PDF and CDF FT and FT, PDF and CDF. Now they are asking what is the first property? First property is RT is equal to integral T to infinity FU du for T greater than 0 and 0 otherwise. So here, what the definition? What the definition we have for the reliability? Reliability is what? Just now we have seen. It is a probability that time to failure must be greater than T. So by the definition, what is this? This is the integral from T to infinity of FU du. The same they have asked, right? So it is reliability is nothing. It is the integral from T to infinity of FU du. Then in the second part, where F is the PDF of the T, in the second part, R dash T is equal to minus FT. R dash T is equal to minus FT. Now, RT is equal to, if you integrate this, it is what? It is the FU T to infinity, and it will become the F infinity minus FT. And what is the F infinity? For any probability, what is the F infinity? For
One.
any density function?
It is
Yes,
one.
TDF at it's 1. 1 minus FT. So if you differentiate on both sides, dr by dt, so it will become minus d by dt of the ft. And what is the d by dt of the ft? CDF, derivative of the CDF is the PDF. So minus ft. So r dash t is equal to minus of ft. So we have the second relation. Then in the third, RT is non-increasing function of t. RT is non-increasing function of t. So if you take, let t1 is greater than 0, which is less than the t2. So if you compute what is the rt1, what is the rt1? By definition, rt1 is what? Probability t greater than t1. So it is what? t1 to infinity, t1 to infinity, fu du, fu du, and this can be written as t1 to t2 fu du, or this can be written as t1 to t2 fu du plus t2 to infinity fu du. And what is the second expression? t1 to t2 fu du plus what is this expression? This is the probability t greater than t2 and t1 to t2 fu du plus what is this? rt2. So here it will give you rt1 minus rt2 is equal to t1 to t2 fu du. And what is the nature of the f pdf? What is the nature of the f pdf?
Non-negative.
Yes, it is always the non-negative, right? It is always the non-negative. So this integral will come greater than or equal to 0. So this will give you rt1 minus rt2 greater than or equal to 0. It means this implies rt1 greater than or equal to rt2. So this implies non increasing function, non increasing function of t, non increasing function of the t, right? So reliability is with respect to time always decreasing or remain constant. Never be never with the time reliability will increase. With the time, never the reliability will increase. Reliability can increase after taking some measure, preventive measure, corrective measures, right? Then only you can increase the reliability. Means you are changing the condition. Under the particular or specific condition, reliability can never increase. Then after, fourth is r0 is equal to 1 and r infinity is equal to 0. So we know that rt is what? Rt is integral t to infinity fu du. So if you have to compute the r0, it means it will become the 0 to infinity fu du, and it is what? It is the means complete time for the failure. So its integration will give you 1. Then after, if you have to compute the r infinity means limit b tends to infinity, b to infinity of fu du, or you can say in layman it is the infinity to infinity fu du. When we have the upper limit and lower limit same, so its integral will be the 0. So r infinity will be the 0. Means after an infinite time the reliability will definitely fail. Nothing is immortal. Even human being also cannot survive. Means after the infinite time human being has to die. So there is no device right? We can manufacture which has the infinite lifeline. After the infinite time, always every device has to fill. Then after, we have the RT is equal to 1 minus FT, where FT is the CDF or unreliability. So already we have seen reliability is what? It is the integral t to infinity fu du, which can be written as 1 minus integral 0 to t fu du, and it is what? 1 minus f of t, f of t. So reliability is, and f of t is what? It is the CDF. It is CDF, and also known as the unreliability. Also known as the unreliability. So anything in this theorem you want to ask related to the reliability? Now, after that, we have the very important term conditional failure rate or hazard rate function or instantaneous failure rate at time t. Means at the particular time, what is the failure rate? Up if up to the time t there is no failure, so at that time t, what is the failure rate? That is known as the hazard rate function or instantaneous failure rate or conditional failure rate. So in reliability, it is very important thing, right? So here what I'm saying, that conditional failure rate we define as the conditional failure or hazard rate function is very useful function in reliability. We denote it by the either the ZT or HT, and is defined as ZT we defined as limit delta t tends to 0, means for the very small time, probability or conditional probability that time to failure, capital T is what? Time to failure lie between t to t plus delta t when t greater than t divided by the delta t. What is the meaning? Means here we have the anytime t, here we have the t plus delta t. So up to here there is no failure up to the t, because capital T is given to you, capital T is given to you, t greater than t, means up to and capital T denote the time to failure, capital T denote the time to failure. So up to the time t, up to the small time t, small t, there is no failure, there is no failure. Failure is after the small t and in the small interval of time delta t. So zt denote that it is the rate. Rate means divided by the delta t. Rate, or you can say it is the conditional probability that time to failure lie between t to t plus delta t when t greater than small t divided by the delta t. So we call it as a hazard rate function or the instantaneous failure rate. Means at this instant, what is the failure rate that we are computing? So using the conditional probability, we are writing this hazard rate function. So it can easily be shown that ZT is equal to FT upon RT. Right? We can say that what is the FT? PDF of the PDF of time to failure, and RT is what? Reliability of the device. So we can show the reliability of the device or you can say that zt is equal to ft upon rt. So why the definition? What is the zt? Why the definition? What is the zt? It is the limit delta t tends to 0. It is the conditional probability. What is the given condition? T greater than t. Conditional probability means one condition is given to you. What is the condition? That time to failure lie between t2 t plus delta t. T2 t plus delta t. Clear? So by the definition of the probability of a given b is equal to what? Yes, probability of a given b is probability, right? A intersection b means t2 t plus delta t intersection t2 t greater than t divided by probability of t greater than t and 1 upon delta t. Conditional probability means p a given b is equal to p of a intersection b divided by the pb. Clear? So if we have, this is the t, right? This is the uh, uh, t plus delta t. So if I say t lie between, this is the t, so t lie between t to t plus delta t and t greater than t greater than t. So what is the intersection of these two things? What is the intersection of these two things? T between t to t plus delta t and t greater than t. So what is the intersection? What is the intersection of this and intersection of this? So intersection will be this only. So this can be written as limit delta t tends to 0, probability t less than equal to capital T less than equal to t plus delta t upon probability t greater than t and 1 upon delta t. This can be written as limit delta t tends to 0, probability of t less than t plus delta t minus probability of t less than t divided by delta t 1 upon probability t greater than t. This can be written as limit delta t tends to 0, 1 minus probability t greater than t plus delta t minus 1 minus probability t greater than this t upon delta t 1 upon probability t greater than t. So what is this? 1 and 1 cancel out, 1 and 1 cancel out. So what is this? This is the reliability. So this can be written as limit delta t tends to 0. Here we have the minus minus plus. So rt, or you can say minus if you take common. So r of t plus delta t minus r of t divided by the delta t and 1 upon probability t greater than t. So what is this? What is this? First principle of
R dash
derivative,
T.
r dash t. So this is the minus of r dash t divided by the rt. This is what? Rt. And just now in the theorem 6.1, we have seen r dash t is equal to r dash t is equal to minus of ft. Minus of ft. So when we put here minus of ft, it will become the ft upon rt. So zt is equal to ft upon rt. So here we have the relation between the hazard rate function, PDF, and the reliability. So from the above equation, it follows that for a small time delta t greater than 0, some positive time, zt into z2 into delta t will become, it is a conditional probability that time to failure lie between t to t plus delta t, means device will fail at that instant in the small time interval when it is survive up to the time small t. Thus for small delta t, zt into delta t approximate conditional probability that device will fail during the interval t to t plus delta t. Means device will fail in the interval t to t plus delta t, given that it has survived up to the age t. It has survived up to the age t. In other words, failure rate zt approximate probability of failure of a device in a unit time, when in a unit time following the instant t, if it is working up to the time t, or it represent proportion of the failure in the interval t to t plus delta t out of those surviving at time t divided by the delta t. Means if you have the number of device, so it is in the relative frequency approach, if you are want to write, so number of device fail in the interval t to t plus delta t out of number of device survive up to the time small t divided by the delta t. So in particular, if I say z2 is constant, right, zt is hazard rate function is constant, it implies that probability probability of time to failure lie between t to delta t, given t greater than t will become the lambda into delta t if zt is constant. So when the zt is constant, what this implies? So thus in this case, the probability that the device will fail in a small interval t to t plus delta t, given that it is surviving at time t, is independent of the time t. It is independent of the time t. Means here in this expression, there is no small t. Only we have the this small interval delta t. This small interval delta t. So what this implies? Whatever the big time or small time here, it is immaterial. If it is independent of small t, whether it is survive up to here or whether it is survive up to here, it is immaterial. Failure depend only on the interval, right? It does not depend how from what time it has been started. So it is given to you, given that it is surviving at time t, is independent of that time t and depends upon the length of the interval only. it depend only on the delta t. It is independent of the time t. In such cases, it is natural to say that device is as good as new at any instant t of its life. Means टीवी हम कब कहते हैं कि खराब हो गया? जब वो खराब हो जाता है. जब तक वो चल रहा होता है हम ये कहते हैं ये बिल्कुल नया है. ठीक है ना, भले ही वो 1 साल पुराना हो, 2 साल पुराना हो, यदि वो चल रहा है, देयर इज नो मिस्टेक, तो हम कहते हैं कि इट इज वर्किंग. So means the device is as good as new one until unless there is no fault. Now, following theorems give the method of determining the FTRT from the ZT. We have the relation of the ZT, FT, and RT. So, if the hazard rate function is given to you, how you can compute the FT, right? And how you can compute the reliability. So for that we have the theorem 6.2. If T is time to failure, random variable, continuous random variable of a device with PDF characterized by the PDF and CDF, probability density function and cumulative distribution function, small f and capital F, and we know that F0 is equal to 0. ZT is the failure rate function of a device, means hazard rate function, instantaneous rate function, or conditional probability. Then reliability in terms of the ZS will be the reliability is equal to e to power minus integral 0 to t ZS ds, and ft is equal to z2 into e to power minus integral 0 to t ZS ds for t greater than 0. So we know the relation. Just now we have seen
Huh?
Z is yes,
Sir,
yes,
it's
yes.
already 8:56.
Okay, okay, okay. I'm stopping. Okay, next class I will continue. I have not seen the time. Sorry.